Welcome to Thermodynamics. Today we'll be solving ideal Brayton cycle problem. Given as air is the working fluid, enters the compressor at a mass flow of 5 kg. The pressure of the inlet compressor is 100 kPa. Exit pressure is 12 times the inlet. The inlet temperature is 300 Kelvin as given here. Exit temperature of turbine is 1400. Furthermore, more statements are given here. Let's get started and go to thermofluids.net, which I'm already here. We select the vapor, power, and gas power cycle. It's a PG model. Let's get started. Okay, so what do we know about state 1? That pressure is equal to 100 kPa and temperature is 300, and we also know the mass flow rate is 5 kilograms per second. There we can calculate state 1, state 2. State 2, we know that pressure is 12 times P1, and what else we know? We know that it's isentropic compression, so therefore S2 is equal to S1. Mass flow rate stays the same, m dot 1. We can calculate this state. State 3, we know that pressure at 3 is equal to pressure at 2. We know that maximum temperature, which we will go to IO panel and define here as Tmax equal to 1400 Kelvin. And enter. We go back, we can declare as a Tmax. As we hit enter, on top it shows that it's 1400 Kelvin. As I earlier said, pressure at state 3 is equal to pressure at 2, and we also know the mass flow rate is still same. There we can calculate the whole state. State 4, we know it's equal to pressure 1. Also we know that it's isentropic is equal 3 and mass flow rate. Therefore we have calculated all 4 states, and let's just make sure and go to graphic panel and make sure it looks like how it should be, where we can see from state 1 to state 2 is isentropic, state 3 to state 4 is also isentropic. We can go to device panel and calculate all, complete the cycle basically. And this is state 1 to 2 where no heat generation, therefore we can calculate the work of compressor. Device 2, that goes from state 2 to state 3, there's heat generation, no work, therefore that. Device 3 would be state 3 to state 4 where no heat generation, and that's the work of turbine produced. State 4, and next one we can go to device 4. Device 4 would be the last state. Goes from state 4 to state 1 back with no work and heats out. Therefore we go to cycle panel. We can make sure it's a cycle status is complete. This is all the calculation we have found. So this is the total work output to 2014 kilowatts. Thermal efficiency of the Brayton cycle is approximately 51%, and we go to IO panel just to make sure we can get it here too. This I already had it typed up just for the time. Basically this is the work W dot compressor, ideal work of the compressor. It's heat in, ideal work of the turbine. This is Q out, there's Q net, and Where's that? Finding all the calculation in here, as we can make sure in the in the cycle panel the thermal efficiency is about 51%. Here we can also make sure it's 51%, just to be sure that we're doing it correct. So therefore, to move further, we can go to, okay, let's go back to the PowerPoint. What if scenario. What would be the system efficiency and power output if the maximum temperature is 2200 K and pressure ratio is 8? Temperature about 2200, which we can do it here. Enter. Also pressure ratio, which is 8, which we can go back to the only state that's reflected with the pressure ratio is state 2. There we can say it's pressure ratio multiplied by pressure 1. Here it shows us new pressure here, so it's 8 times the pressure 1 was 100. The states calculated. Let's super calculate it. We can go back to the cycle panel and therefore see some changes in here. Thermal efficiency has been decreased to 44%. Total work output has been increased to 3725, where earlier it was 2000. Also, we can make sure here 44% and total output is 37. Thank you for watching this video.